Now I would like to, so I'm going to start. Okay, so I'm going to cut the video here into two parts, just now and for 1 hour, and now for 1 hour. All right. Okay, let's begin, guys. So welcome back. This is week 9, and this is a second hour. So this is 9.3, week 9, the third hour of our recording, and we are 18th of October 24, and we'll begin complex numbers. And we are going to introduce only what is a complex number in this lecture. And let us see the slides. Now it's called chapter 8a, and we have an overview, and this, in this overview we are going to do this today. The introduce, and it's very gentle. We are just going to define, introduce some operations, add, multiply, subtract, divide. That's it. And when I was preparing for this course, I went through all this. Okay. And the nicest one, I mean, I depends on you, of course. I like Petra. Petra is wonderful. So, but it's up to you. It's totally up to you. Now, if you want a very hard introduction to complex numbers, and you see a different speed that they are doing. Okay, guys, look at Oxford, right? And of course, you can also see Brunton. I like Brunton, but Oxford is very hard. So these are online, and these are references for you for PDFs, right? So you don't need to never buy a book again. Just use everybody one. Lemar, Paul Lemar is very, very nice. CUHK also. So Habimat. So I only put the nice one here. And I put Oxford one because I want to show you how difficult things can be. Okay, so let's see. And you realize that everything is done on on a on a on the on a whiteboard, huh? So nice, right? So so this is how, I mean, the old days I learned anyway. But yeah, so this is, that's why I'm writing now and talking to you. So in fact, I believe that learning like this is wonderful. But this is very fast. Okay, so and it's called an introduction. First year. Okay, guys? Right, so you're in great company here. Okay, now with that, let's begin our problems per se. So I'm not going to do the same thing as I've done in my YouTube videos. Otherwise, there's really no problem. No point, I mean. So what you will see is that I will do this at a different speed, and hopefully uh we have a dialogue and you can tell me what's the problem. Okay? Okay. All right. Okay, let's begin. Let's begin with the number line. Everybody seeing my screen? Can someone type, please? I'm recording. Yep. Anyone type something? Okay, great. This is the number line. And when we were dinosaurs, we when we were in the dark ages, we only know the whole number, 1, 2, 3, and it took a long time to figure out that 0 was important. And then of course, then everybody wanted to invent negative numbers so that we can owe money to other people, right? So the number lines looks like this, and yeah. And then of course, everyone figure out that we need half a cake, right? Half. We need, one half of something. So we introduce fractions, rational numbers. So we have the integers first. Oops, we have the integer. So this was the integer. Then we have the rational. Then what else do we have, guys? After the integer. I is a set of all integers. This, and then Q is half, right? 2 3/4. These are Qs. Some more, guys. After I and Q, what do we have? What other? This is the number line. Come on, guys. After I and Q, irrational. Very good. Give me one irrational. Yes, one example of irrational. Pi, 3.14. So here is pi. 3.14, blah, blah, blah. No n. Square root of half. Yeah, 1.414. Somewhere here. Square root of half. Yeah, whatever. So you realize that now, so what is this set called now? I and Q. After that, what do you think I will write? What is the next number? The next set of numbers. Real number. See? And the real number fully covered. There is no hole in this number anymore. There's no gap in this number line. Any point, there's a number. There's a real number. Okay? The real number encompasses everything in this red line. It's called the real number line. All right. So if I want to write 3, so this x equals to 3 is here, right? Now someone come along and say that the number line is not enough, right? And then they are going to introduce a complex number. So if this is the real number line, I'm going to introduce another line called the complex line, complex number line. How would I draw this, guys? If you are in the 16th, 17th century and you're sitting here thinking, I have a number line, I'm going to draw another number line. Okay? Where do you think the number line would appear? Yes, very good. And then we call this the complex numbers. And again, the complex numbers, because we already know how to, that, they should also be, and they should also be fully occupied. So along this green line is also a number line, a real number line, but we call this J, and this call this 1J, 2J, and 3J, and minus 1J, minus 2J, minus 3J. And of course, anything in between is still okay, because I should be calling it alpha J, where alpha belongs to the real. So maybe I can have J pi. Where's my J pi? 3.14. Oops, here. J pi. J 3.14, blah, blah, blah. See? So now I have 3 here. I have J pi here. What do you think this number is? It is Z equals to 3, right? Real number. Plus J pi. Where is this? So this number is 3 along the real axis, pi along the imaginary axis. So this is imaginary axis on the vertical line. And the red one is the real axis. And this is the convention, right? And this whole thing is called the Argand diagram. And we call this the whole thing the complex one. There's a name. It's called the complex plane. We call this the real line, right? The imaginary line. But two of them forms a plane. Call this the complex plane. So what's the notation now, guys? IQR, the next symbol is called the complex symbol, the complex. Yeah, excellent. The funny little looking C. Okay, very good. So great, isn't it? We're now living in the 21st century, and we realize that, hey, we have C, the complex plane. All right, so what is the notation we use? We use C as the set of all complex numbers. What are the complex number? Equals to A plus JB. And what? A belongs to real. B belongs to real. J equals to the definition of J, guys. What is the definition of J? We haven't tell you, huh? We just say that square root minus 1. All right. So we have so we so but then we are wondering where the hell is square root of minus 1, right? And we just created this out of thin air, right? Later on you'll find some square root of minus 1, and then you'll be you'll be moving along here. All right. And then what is it for? And then you'll be thinking, why do we even bother? And then the answer is this. Let's have the simplest answer. What is x squared? Oops. Minus 4. When we said x squared minus 4 equals to 0, therefore x squared equals to 4, therefore x equals to square root of 4. Answer is plus minus 2. Okay, guys? Then everybody's happy. We still do not need. And of course, once in a while, you write an equation like this, and then you go like this, and then you are stuck because all you could do was this, and then all you could do was this, and then all you could do was this, and then you said, hey, that because square root of minus 1 came about so often, define. Of course, sometimes equals to I, sometimes equal to J. You'll realize that I introduced I and J. It doesn't matter. The mathematicians use I, the electrical engineers use J. Doesn't matter which one you prefer. So we realize, okay, it has a use after all to solve for equations that that have square root of negative numbers. Okay, nice. All right. Now, then you look at this. Okay, you look at this, and then I'm going to now solve. I'll show you exactly where the roots will land. Okay, guys? Oops. All right. Let's have this picture. This is a second, a polynomial order 2, and we can solve by using these equations here. And here, this blue thing, of course, is this equation. How do we know? We just substitute different x, and we get the blue line. And you guys have to be very intuitive about it. When x goes to infinity, infinity times infinity is infinity. That's why he goes this way. What about negative infinity? Negative infinity times negative infinity, also infinity. So he looks like this shape. And because then, interestingly, when we draw this shape, we are very interested to find when y is equals to 0. When y equals to 0, you will touch it at these 2 points. These are called the roots of the equation. And he touches at minus 1, and he touches at 3. So you could substitute minus 1 here. So minus 1 square, you could substitute minus 1 here. You work it out, and this equation becomes 0, as expected. You substitute 3 into this equation, you also go to 0. Nice. So this is 2 real solutions. The word solutions is talking about the roots. The solution or the number x that makes the equation 0. Now, we start to move things around. We change the equation a little bit. And it goes like this, and then suddenly this whole curve goes up, 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 up. And then now we only have one solution. So only one value, only one x will make this whole equation equals to 0. So this is called a repeated solution because the fundamental theorem of algebra tells us if this is second order, we'll have two solutions. So we call it a repeated solution. Now, as we move, we change some more numbers, the whole thing goes up. And then there is no more solution. Okay? But actually there is two complex solution. All right, let us figure out where it is. This is a very nice diagram of x squared minus 6x plus c. X squared minus 6x plus 9. Okay, this is the equation. So in x squared minus 6x plus 9, c is 9. He will show you that he will be hitting at x equals to 3. And this 3 is a repeated solution. This guy. Okay, please watch this YouTube. Nothing to do with me. And you'll realize that when we have different c, when c is 8, the whole curve goes down. There is two roots. This black line is the real line. Okay, the real line. So it has two solutions, 2 and 4. When c is equals to 9, the curve moves up and the answer is only 3. When c is 9.5, the curve moves further up. Now there is no more real solution. We are told that there is two complex solutions. Where are they? And the answer is, it's still sitting at 3, but now with complex numbers sticking out. One of them is plus j 0.707 minus j 0.707. So this is the magic, right? If you are observing the function in the complex plane, you can see where the roots are. Here in the real line, you are still stuck with this black guy, and all you can see is if there are two real roots, you have one real roots. But once the curve goes up, you couldn't see where the roots are. But if in the complex plane, you see exactly where they are. Wonderful, isn't it, guys? So now you at least can see where one of the very nice visualization. Okay, so let's hit this and see whether it's still alive or not. Yep, so it's still alive. Go and have a look. It's wonderful. Yeah. All right. So we figure out what we can do with what do you call that? A complex number now. Okay. So some revision, guys. Mm, radical. This is O level, A level. Square root of A and B equals to. Someone tell me, please. A and B are real numbers or whatever. Square root of A, square root of B. Okay. Square root of A over B, square root of A over square root of B. Okay. Square root of A, square root of A, square root of A, square root of A square, A. Okay, so you need to uh, revise all this because we're going to play with a lot of complex numbers. Okay. Arithmetic. 8a.1.3. Z belongs to the complex number. Z is equals to A plus JB. AB real. What can we do? Plus and minus. Let's have Z1 plus Z2. So Z1 is A1, A1, A1. Z1 equals to A1, B1. What about this guy? So of course it's A1 plus JB1 plus A2 plus JB2. And then we can collect the reals and we collect the imaginary, and then we're done. And then if this is plus, we're done. And if this is minus, oh, sorry, what am I doing? Okay. So what I'm saying, Z1 minus Z2 is this guy minus this guy minus this guy. Eh, sorry, what am I doing? Let's forget about this. Let's just brute force. Z1 minus Z2 equals to A1 minus A2, right? Plus J B1 minus B2. Come, yeah, let's not be smart about this. So we now know how to do addition and subtraction. Okay? Now I'm going to introduce division is a very hard exercise, guys. Let's do multiply first. How to do Z1 multiply with Z2? A1 plus JB1 multiply A2 plus JB2. You can do brute force. A1, A2 plus J, A2, B1 plus J, A1, B2 plus J square, B1, B2. Okay, you can do it this brute force. Yeah, of course. In fact, this is our definition first, right? Then equals to, then you collect all the reals. A1, A2. This is the real. This is also the real because J squared equals to, guys, J squared is J is what? J equals to root minus 1. J squared equals to root minus 1 equals to minus 1 minus 1 equals to 1. Equals to minus 1, right? Minus 1. J squared is minus 1. B2. Okay, and then plus J. 2. So not 2. J A2 B1 plus A1 B2. So you can do it this way, but this is horrible. So multiplication will never do this in, what do you call that? In, what form is this called, guys? This form is called the rectangular form of complex number. Why do we call it the rectangular form? Because if you look at the picture, it is like forming a rectangle in the complex plane, moving along the real axis and moving along the complex axis, the rectangular form. Okay, so we know that it is easy to do addition and subtraction in the rectangular form. To do multiplication in the rectangular form is very hard, and we'll never do it this way. So what should we do, guys? I think to to share with you, I need to do in something called the polar form. Okay, let's introduce this first. This is A. This is the real part of Z. Z equals to A plus JB. This is the real part, right? And this is the imaginary part. Therefore, this is This is JB. Where is A plus JB? This point. We call this D. So this is Z belongs to the complex plane. I find where real is, I find where the imaginary is, the intersection between these. Yeah, yeah, guys. Right. Okay, there are some questions, but let's finish this first. A plus JB. So Z is a point in the complex plane. And this form is called the rectangular form because as you can see a rectangular here. Isn't there another way we can think of? We can think of this Z as a vector forming an angle and and it has a magnitude or modulus R, where R is equals to what? The modulus of Z, and the modulus, the length of Z, is defined as in the Euclidean space is a square plus b square square root, because this is a right angle triangle, and theta is in radian, and anti-clockwise means what? Positive angle. So maybe here is, let's say, 60 degrees, for example. For example, 60 degrees. But we don't like 60 degrees, of course. So you go and convert into 60 degrees, whatever number you think, in radian. All right. So therefore, couldn't I write Z is also equals to R? Isn't this so nice? I mean, A plus JB is moving along the rectangular, the two axes. R theta is saying that I have a length R with an angle theta. Notice that R is positive, huh? It can be zero, of course, but it's positive. It doesn't need to be negative because all I need to do is change the theta so that I can move anywhere, right? Okay, so that's why R is equals to absolute value of Z. So this guy is a positive number. Now, if you have these two forms already, so I have the form number 1, oops, and form number 2. So this is called the polar form. What? Number 3, guess. Z equals to, right? This is the polar form, right? But, but couldn't I get A and B back from R and theta? Right? So what is A, guys? A is R cos theta, right? And what is B? B is R sine theta. Okay? So this is the third form, the trigonometric polar form. There's one more form, okay, guys? Later on. So you realize that this trigo form and this complex exponential form are actually the same because we introduced the Euler identity Ej theta equals to cosine theta plus j sine theta. First, we introduce this identity, then we can plug it in. Then when we open up this, it is exactly this. And number 3 is exactly inspecting this guy to say that A is R cosine theta, B is R sine theta to get back this. So you realize that, hey, in this one nice picture, I show you 4 different ways to write the complex number. Okay? Now, there's a small problem, and the problem is this. A, B. A plus JB. This is R, this is theta. R, theta. So far, okay, guys? Everyone happy? Then my question to you is, how many ways in rectangular form can I write the position of Z? How many ways? Z equals to A plus JB. For example, A is, let's say, 1, B is 2, so this guy is Z is equals to 1 plus J2. There's only one way in rectangular form, right? No other way to define this. What about here? What is R? Theta. What is my theta? Opposite over adjacent, right? Arc tangent, what? Opposite is 2 over 1. So some value here. Everybody happy? Yeah. What do you say? But, but what, guys? What happened? This value, whatever it is, plus 2 pi. Yes. So theta is here. Theta plus 2 pi is here. Theta plus 4 pi is here. Same. K. K equals to integer. Positive integer, negative integer. So this is a very strange thing uh, that you will find in complex numbers. In rectangular form, there's only one way. In the polar form, wow. Okay, any theta plus 2 pi k multiplying by the modulus give you the same point. And this will create very rich mathematics, and hopefully we'll have a chance to visit that. All right. Now, why did I introduce the polar form? Because it must be of use. And the reason was in multiplication and in division, Z1 multiplied by Z2 is very nice. And Z1 divided by Z2 is very nice. Now, without proof, guys, otherwise you will be here the whole day. Z3 equals to Z1 times Z2. Z1 is written as modulus of Z1 angle theta 1. Okay? So you go and convert your number rectangular into polar form. Z2. And then what do you think what's going to happen, guys? The modulus multiply. The angle, guys, adds. Okay? So it's very nice. Z1 times Z2, the the modulus, the length multiplies, the angle adds. Let's pull out our slide. Where is it? Here. Z1 is here. Z1 is R1 theta 1. Z2 is here. R2 theta 2. Z3, which is Z1 times Z2, it is R1 times R2, the length, theta 1 plus theta 2. The proof is here. Okay? All right. So this is the take-home message. And yeah, I mean, to prove this, you have to do all this. But it's not very exciting. What about division? Division, again, notice that I put it in this form. But I prefer my shorthand, R1 angle theta 1, right? I don't need to write all this. So Z1 divided by Z2, it is basically the modulus divide and the angle subtracts. So this is a take-home message. So now when you will go back to our slide here, the operations that we are interested in, plus and minus, we always do in rectangular format. And the divide, we are always, we'll throw away all these guys and we'll write two equations. Modulus Z1, modulus Z2, theta 1 plus theta 2. Z1 divided by Z2, modulus Z1 divided by modulus Z2, theta 1 minus theta 2. So nice. So this is the four things that we do. Plus, minus, multiply, divide for complex numbers. Okay, we are almost done. We have one more slide left for complex numbers. And in next week, we are going to do much more exciting things. So this week, we are only introducing the very basic operations and the definitions. And yeah, just now I had some questions of square root. So j is equals to square root of minus 1. J squared equals to square root of minus 1 times square root of minus 1 equals to minus 1. Okay? But actually, if you so let's try. Z is equals to 0 plus 1j, right? Say what? Okay. Z is equals to j, basically, right? In polar form, guys, how would I write Z? This is the rectangular form, right? Or Z equals to j, which is Z equals to 0 plus 1j, which is equals to, what do I write? The modulus, angle, what? Where is j, guys? So in the plane, this is the real line, and this is the imaginary line. This is, of course, 1. This is 2. Minus 1, minus 2. This is j, 1j, right? This is minus 1j. So j is sitting here, guys. J equals to z. So his length is what, guys? His length, 1. His angle, theta equals to pi over 2, 90 degrees. So it is 1 angle pi over 2, right? If you write it in 1 cosine pi over 2 plus j sine pi over 2, what do we get, guys? 1 cosine pi over 2, 0 plus j, 1, j. So actually, whenever you're writing complex numbers, please remember to draw your complex plane, and then you get this guy. So let's call this Z1. Z1 multiplied by Z1 is equals to, let's take this guy, 1 angle pi over 2 multiplied by 1 angle pi over 2. What do we get, guys? 1 times 1 is 1, right? Pi over 2 plus pi over 2 is 1 angle pi. Where is pi? I'm going to use the blue. Pi is here, right? Pi is 180 degrees. Agree? And magnitude is 1. Who is he? He is minus 1, right? Because this is 0, 1, 2 on the right-hand side. 0, minus 1, minus 2 on the left-hand side. So now you realize that actually minus 1 can be represented as magnitude 1 angle pi. Or I should write 1 cosine pi plus j sine pi. And later on, you write 1 ej pi because ej pi cosine pi plus j sine pi. So, so now you realize that we're writing numbers in so many different forms, and that is why it's confusing. But the different forms allow us to do the operations more easily. Okay? All right, so I diverge. So I have 5 more minutes left, and I'm going to do complex conjugation. Or shall we do it next week, guys? How's that? New messages. Oops. Anyone? Next week? Okay. But okay. I mean, since you are responding, that's good. So I'm going to ask you all to tell me, okay, is this, where's my, yeah, I'm really interested to introduce, no, to get feedback from how to improve your learning. I mean, linear algebra. You'll realize that I'm putting my recorded lectures here. So I'll put whatever we have today here. I haven't done my complex numbers, but I'll do it soon. So the complex numbers are here. And I mean, just go through them and see. So I'm going through exactly the same thing I've gone through in these recorded videos, but at a different speed. Okay. So hopefully you see I explain the same thing in different ways. That's all. Yeah, maybe I think it must be quite. So let me know how to improve your learning. Oops. Lost in complex numbers. Okay, why are you lost in the complex numbers? Which part is difficult? Okay, I'm going to try to do complex numbers in 5 minutes. Okay, guys? Oops, I can't see. All right, I'm going to. Okay, complex numbers can be very difficult, but actually, when I watch, what's her name? Petra, right? Click this link. Watch her, and you do not need to watch all. Huh? You only need to watch 1, 2, 3, 4. Okay, about 1.5 hours, the most. In fact, I mean, she did everything that I want to do in maybe 30 minutes or 40 minutes, but she's very clear. Okay, and she did it in examples and numbers and things like that. So for those guys who have problems, and yeah, Petra is great. All right. Okay, so watch her. for those who have problems. And if you really, really am keen, just watch Oxford. So with that, I'll see you again next Monday. And if you all are here, please remind me to to what start the recording. Okay? And with that, thank you very much.